Hello everyone, my name is Nikola Marincic. Welcome to another class of our course, An Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are now in week 7 and we have completed a large part of our course which involved multivariable calculus and coding, so I won't be doing a recap today. And also today we are starting with something entirely new and hopefully exciting for you, especially if you're an architect. And this is the diagram of the neural network that I asked you to implement on your own. And if you did so in a way that we learned how to do it so far, then I assume that your code looks a little bit messy. So this is exercise 9 that we did. We implemented this particular neural network. And as you can see, what we did, we instantiated our variables for all the weights and biases, then we computed our forward pass and backward pass. And as you can see, there is a lot of inelegant formulations and code blocks here. And this is because we have been dealing with the weights and biases of the network on an individual basis. So we did not have means to structurally abstract from them. And this was until now. As you will see, linear algebra is a branch of mathematics we can instrumentalize to make our neural network algorithms more abstract, flexible, and efficient. And if you're an architect, then this particular branch of mathematics might be a lot of fun for you, as it requires some skills in understanding space and spatial transformations. And to start our short linear algebra journey, we will start by introducing vectors. If you remember this example from calculus, it was about the motion of a cyclist. And we investigated the idea of speed as a relation between distance and time. And distance, in this case, was a non-localized distance. This means we did not really care where does the bicycle go as it moves, where does it start, where does it end. It could go to the west, east, north, but we do not really care about that in this example, as long as the bicycle traversed the distance of 300 meters. So let's see what happens when we try to localize this distance. So this is the aerial map of the ETH campus. And to even think about distance in this picture, we need to land on this side, yeah? And also we will assume that the terrain is flat, although it isn't really flat. So then let's mark a few locations on this map. And let's think about what would distance mean geometrically from the perspectives of these 4 points. What we could do is we could represent distance with a circle around our points. So at point 1, we will mark the distance of 100 meters. With the point 2, we will mark the distance of 200 meters, point 3, 50 meters, and point 4, 75 meters. So what do these circles indicate? Well, circles indicate all the points that are equidistant from our starting point, or in other words, all the places that are exactly 100 meters away. But the question is, what distance here does not allow us to do? Well, distance here cannot help us to describe a movement from A to B. Yeah? We cannot address displacement. So to address displacement, what are we actually missing? So what we are missing is direction. So some quantities and processes that we can observe do not depend on the direction in which they occur. For example, length, area, volume, speed, mass, energy, density, entropy, temperature, pressure. These are kind of quantities that does not depend on the direction at all. For example, if something has a certain volume, if we move it to the left or to the right, the volume stays the same. It is not dependent on the direction. But some other processes or quantities, they do depend on direction. For example, displacement, moving from A to B, or velocity, acceleration, momentum, and what you have learned in school, forces. Forces always have direction. So what does direction here mean? Well, it means picking a single point on a circle. So instead of infinite number of points, now there is only one point that you're interested in, and this point introduces direction. Well, with this direction, I can describe that I'm standing in the middle of the campus, and I'm looking at the physics building, for example, which is 100 meters away. And of course, for any point in space, I can decide to take entirely new direction and length. Also, I'm entirely free to move these vectors wherever I want within this space. So these quantities that I represented with arrows, and then I change them and move them around this map, we call them vectors. And they can be freely moved in space and localized wherever we need them. But if we wanted to compare vectors, then this ability to be represented anywhere, so they can be on the left, on the right, on the North Pole, in your bedroom, well, if they are localized at different places, how can we actually compare them then? Well, what we need to do is we need to move them all to the same point, and this point is the coordinate origin. To be more precise, vector's starting point needs to be at the coordinate origin, and then their tips are not restricted where they will go. So now we can ask when two vectors are actually different from each other. Well, they are different if they have different lengths. So vector which has length 50 meters is different than the vector which has 100-meter length. So even if they point at the same direction, their lengths make them different. Also, vectors will be different if they have different directions. So they can all be 50 meters long, but if they point in different direction, then they will be different vectors. And now we can also ask the opposite question. When are vectors equal to each other? Well, they are equal if they have the same length and point in the same direction. And now let's see how we can represent vectors. So one way would be to measure their angle with the horizontal axis and their length. And this is called polar representation. But what is very unique to linear algebra is to represent vectors in terms of their projections into space. So if this locality into which we submerge vectors has two dimensions, then our vector will have two projections. Projection in terms of the first axis and projection in terms of the second axis. Then we store these projections in an ordered list, so it is very important that they are stored always in the same way. And if the space has 3 dimensions, then we will have 3 projections, and very importantly, if our space has n dimensions, so any number of dimensions, then we will have n projections. Here we have some concrete vectors. We have 4 two-dimensional vectors, and their tips are marked by a pair of coordinates. So to reach the tip of the vector A, we have to move 3 units along the horizontal axis, and then 4 units along the vertical axis, or vice versa. And to reach the tip of the vector E, we go 2 steps along x, 3 steps along y, and then 5 steps along the z-axis. By using this convention, each vector becomes uniquely associated with a list of numbers containing the coordinates of its tip. Because of that, we can represent these vectors symbolically. And here is the convention. So we mark the variable containing a vector with a lowercase letter, and then we put an arrow above it. And then we store vectors' coordinates in a single column of numbers within square brackets. The top number will indicate the first projection, the second number will indicate the second projection, and so on. And now let's see how we can do this in Python. Here is our exercise number 10. And we have a number of vectors here on different dimensionalities. So let's do what we are asked to do here. So import NumPy library. Import NumPy as MP. It says by using NumPy arrays, represent the vectors A to E. Well, we have been already using NumPy arrays, but we did not really know that they are actually representing vectors. Well, now you know. So let's represent them. So how we can do it? So let's write mp.array and then open square brackets. And if I type this, I would get a vector represented as a row of numbers. But I want a vector which is actually represented like a column. So what I need to do, I need to surround 3 and 4 in additional brackets. When I do that, I get now a vertical arrangement of numbers, yeah? And now I need to assign it to A. So A will be equal to this array. All right. And now we need to represent B, C, D, and E. So I will just copy A a couple of times and change the numbers. So B, C, D, E. This one is 2, -1. The third one is -3, -3. Fourth one is -2 and 3. And the last one is 2, 3, and then add another one, 5. All right. It says print the values of some of the vectors to make sure they match the definition. So I just want to make sure that my E variable will give me the same thing as this, for example. So if I say print E, I have 2, 3, 5, and this is the same. And then if I print A, it should give me 3, 4, 3, 4. All right. Here we have a vector and we have its coordinates. So how can we compute the vector's length from this information that we have? First, let's project the vector's tip to our axis. So we can now see 2 triangles on this image, and let's just mark any one of them. So we have a triangle here whose side lengths are equal to the projections 3 and 4. So how can we compute the length? Well, in the most elementary way, we can use the Pythagorean theorem. So what does this theorem tell us? Well, it tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. So the length of the vector A, indicated with the variable A surrounded by two pairs of vertical lines, is equal to the square root of 25, which is equal to 5. So how can we do this then in 3 dimensions? Well, we can start with the xy plane, we can mark the triangle there, and then compute what is the length of the hypotenuse. And it is going to be equal to the square root of 2 squared plus 3 squared. And then we can mark the second triangle, and it is the same story. One side is the square root of 2 squared plus 3 squared, and we add to it 5 squared. And we get that the blue line's length is something around 6.16. As you can see, we are simply adding all squared projections and then just taking a square root of them. A great thing about linear algebra is that this procedure now seamlessly extends into higher dimensions. So let's say that our vector lives in 5 dimensions. Well, then it will have also 5 projections. And you don't have to think about these dimensions necessarily as spatial dimensions, like height, width, or length. Any independent property of an object, such as for example temperature, blueness, opacity, or whatever you want, we can think of it as a dimension. And if you would like to compute the length of such defined object that you defined by means of vectors, you just need to add the squared projections and then finally take the square root of the sum. Let's see how we can compute vectors magnitude in Python. The simplest way to do this would be to use the NumPy's built-in function linalg.norm. And it asks us to use this function to compute the length of vectors a and e. So let's do that. So np.linalg.norm of the vector a. We get that the length of the vector a is 5, as we computed on our own. And the length of vector e is 6,16. So this is using a built-in NumPy function to do this job. Now that we have some idea what vectors are about, let's examine some elementary vector operations. And the first one is vector addition. So let's first examine this operation from the geometric point of view, so without thinking about numbers at all. To add two vectors, a and b, we translate one of the vectors, in this case b, along the vector a, until the starting point of the vector b is at the tip of the vector a. So to get the vector a plus b, we need to draw a line from the origin to the tip of the translated vector b. Or, as I said, we could translate the vector a along b, and we would get to the same point. This property is called commutativity of addition, and it just means that a plus b is the same as b plus a. And this is a feature that vectors share with ordinary numbers. For example, 1 plus 2 is the same as 2 plus 1. And this is not at all surprising. If we have two paths here, and if we want to combine them, we can first move the blue path along the red path and reach this tree here. But we can also first move along the blue path and then move along the red path. We will reach the same point. And then the next operation is multiplication by a number. So here we have the vector u, which we will multiply by the variable a. And we can change the variable a by moving this slider. We will change a to see what happens to the vector which is a times u. Now you can see that when we multiply a vector by a number, we do not change vector's direction. Whatever number we multiply with, it will not change its direction, but it will affect its length and orientation. And this is why in linear algebra we call these ordinary numbers scalars. So if we multiply the vector u by the number 2, the resulting vector will be twice as long. If we multiply it by 1/2 or 0.5, it will be half as long. And the sign of the scalar, whether it is negative or positive, this will not change even the magnitude. This will only change the vector's direction. So if we multiply the vector u by -1, then the resulting vector will be of the same length, but it will point in the opposite direction. Now we come to vector subtraction. And we do not know how to do this, but what we know is how to do vector addition and multiplication by a scalar. So we can use these two operations that we already know in order to define what would be vector subtraction. A minus b, we do not know what it is. But we know that minus b can be represented as multiplying the vector b by a negative scalar, by a number -1. So what we can do now is we can describe subtraction as addition. So we add a to the b multiplied by -1. So here we have a and b, and now we will switch the direction of b by multiplying by -1. This is what we get. So we effectively reduced vector subtraction to vector addition. The only thing which needs to happen is that one of the vectors is multiplied by -1. So we just need to add these vectors now, and we get the resulting vector, which is a minus b. And if we translate this vector back to our original image, we see how they are related. So if we have a minus b, then the vector a minus b will point to the tip of the vector a. If we had b minus a, then this vector will have the same length, but it will point in the opposite direction, and its tip will point to the tip of the vector b. Now, let's explore these same operations from the algebraic point of view. In linear algebra, we care about vectors' projections. So this allows us to represent vectors numerically, even in a situation where we cannot visualize them, like if we had more dimensions than 3. We have the vector a, and instead of looking at it as a geometry, let's just see what its projections would be. So one would be ax, which will give you a number. Another one would be ay, which will also give you a number. And now we can symbolically represent the vector a with the variable a and a pair of numbers ax and ny, which we put in square brackets in a column. Now let's say we have another vector b, and we can extract its projections bx and by. Now we can encode these projections in our variable b. The question now is, what will happen when we actually add the projections themselves, not the vectors? So first, I will add vectors horizontal projections, and then I will add the vertical projections. Of course, one goes in another direction in terms of the other, so we need to subtract them actually. So what we get when we add the projections together, we get a vector which actually ends up being a plus b. So to prove you that this is right, I will just move this vector back to the first image on the left. As you can see, addition performed on number lines representing vectors' projections gives us the same result as adding vectors geometrically. That is a very powerful feature of linear algebra. And now let's see what other numerical operations can we perform with vectors. We can add two vectors together. For example, if we add vectors a and b, this simply means that we add all of its respective components. So we add the first component of a to the first component of b, second component of a to the second component of b, until we have added all the components that the vector has. And here you can already realize that a and b need to be of the same length in order to do this properly. Well, it's the same thing with vector subtraction. We just need to take vectors' components, all of them, and then match them together with the second vector and simply subtract them respectively. Then we have another operation, which is very much used in computer science, but we do not usually learn it in school, which is called vector element-wise multiplication, or a so-called Hadamard product. The sign which we use to mark Hadamard product looks a little bit weird, so you might be scared of it, but in fact the only thing we do is we just multiply respective elements of two vectors. So a1 multiplied by b1, a2 multiplied by b2, and so on and so forth. And the last operation which we will have here is multiplication of a vector by a scalar. So to multiply a vector by a scalar, we simply multiply all of its components by the scalar. That's it. As you can see, all of these operations can be reduced to elementary arithmetic operations on a number line. It's just that in this case, we have multiple number lines for each of our objects. So now vector A in itself contains multiple number lines which are independent from each other. Therefore, to perform the first three operations here, vectors a and b must have the same size. Otherwise, these operations will not work, because we will not have the matching number of number lines. Okay, let's now perform some elementary numerical operations with vectors. We have two concrete vectors, a, 3 and 4, and b, 2 and -1, and we have a real number, p. So what would be then the result of an addition of these two vectors? Well, we simply add x components, 3 to 2, and we add 4 to -1. So what we get is a vector 5 and 3. For subtraction, it is almost the same, except that we subtract elements one from another. So we subtract 2 from 3 and subtract -1 from 4, which gives us the vector with components 1 and 5. Hadamard product just means multiply the matching components, so 3 times 2 for the first one and 4 times -1 for the second one, and we get that the vector is 6 and -4. Finally, when we multiply the vector A by 3, we multiply each of its components with 3 and we get the vector PA has components 9 and 12. There are of course operations which are unique to vectors. One of them is the dot product. And geometrically, we can define the dot product of vectors A and B as a product of vectors' lengths and the cosine of the angle between them. The dot product itself is a very useful operation. It can be used to find an angle between two vectors, to determine the length of the projection of one vector on another, and many other things, for example, for computing the cross correlation in convolutional neural networks. So it is very much used in machine learning. Let's explore it a little bit more. Let's compute the dot product in our particular case. So we have two vectors, one has length 5, the other has length 3. We do not know its projections, but we know that the angle between these two vectors is 30 degrees. So to compute it, we need to multiply 5, which is the length of the first one, times 3, which is the length of the second one, times the cosine of 30 degrees. 5 times 3 is equal to 15, so the product of their lengths is equal to 15, and what changes is the cosine of this angle, and in this case it will be equal to square root of 3 over 2, which gives us the total value for the dot product to be equal to 13. So now if we have the exactly same vectors, but now the angle between them is 60 degrees, we need to practically compute what is the cosine of 60 degrees and multiply by 15. So cosine of 60 degrees is 1/2, so 15 times 1/2 is 7.5. If the angle between this vector is 90 degrees, well, this is a very interesting situation because the cosine of 90 degrees is 0. So 15 times 0 will give us that the dot product for two orthogonal vectors is equal to 0. Finally, if these two vectors are pointing in the opposite direction, which makes their angle between them 180 degrees, cosine of 180 will be equal to -1. So if we multiply 15 by -1, we get -15. So what we can conclude from this? So here I plotted the function cosine of the angle, and I plotted in the y direction the value of the dot product. So what we can observe here, that for certain angles, for example 0 degrees and 360 degrees, we will have parallel vectors, so vectors that are parallel to each other. And for these angles, the dot product will reach its maximum value, its peak. For the values of 90 degrees and 270 degrees, vectors will be orthogonal to each other, which means that their dot product will be equal to 0. And finally, when the angle between vectors is 180 degrees, well, then they will point in the opposite direction. And of course, the values in between also have their respective angle. So dot product here allows us to draw a certain conclusion about how two vectors relate to each other, whether they are pointing in the same direction, whether they are parallel, or they are orthogonal. And now let's see this same dot product only from the algebraic perspective. What would be the algebraic definition? Well, we know that now we care only about the projections, we can forget about the visualizations, and let's say that now we have two vectors with n number of dimensions, so they can have 5 dimensions or 100,000 dimensions. It is only important that these two vectors are of the same length. Well, what would be the dot product from this perspective? Well, it will be the sum of the products of its respective components. This formula might look scary to you, but it is actually much easier than to compute the dot product by looking at the geometrical picture. The only thing we need to do is we need to multiply the respective components, for example, A1 times B1, A2 times B2. We multiply all of them and simply add these products. So that product will actually be A1 times B1 plus A2 times B2 plus all the way up to AN times BN. So let's show a practical example of actually computing the dot product of two vectors. Let's say that we have the vector x with the components 1, 2, and 3, and the vector y with the components 4, 5, and 6. So to compute the dot product, what we need to do is we need to multiply 1 times 4, 2 times 5, and 3 times 6. And then we simply need to add these three terms. When we add them, we get 4 plus 10 plus 18, which actually gives us that the dot product of these two vectors is equal to 32. And now let's just go quickly to our slide where we try to derive vector's magnitude from its projections. What we did last time is we used Pythagorean theorem to derive that the length of this vector is equal to 5. So as you can see, there is a variable a with an arrow above it, and then you have two vertical lines around this a. This simply indicates that this is the length of this vector a. But let's examine this square root here. So we have square root of 3 squared plus 4 squared. And 3 squared and 4 squared simply means 3 times 3 plus 4 times 4. So what does this look like? Well, we have multiplication of two terms, and then we add these two products. So this actually looks like it's a dot product, but it is a little bit of a special dot product because we need to do the dot product of the vector with itself. And then if we take the square root of this, we will simply get the vector's length. So we are now able to describe the vector's length by means of a dot product. Let's just now continue with our exercise. So what it says here is vector operations, adding, subtracting, and multiplying vectors by using code. Okay, let's do it. It says add the vectors a and b. This is actually very easy to do, easier than you might expect. So vector a is 3 and 4, vector b is 2 and negative 1. I can just say a plus b, and I will get the vector, which is the sum of these two. And it says here, print the result of the addition. Okay, print a plus b. So what we get here, we get actually the vector, while here we get this array. So if we're gonna get rid of this array here, you can just use the command print and it will remove it for you. So now it says subtract vector b from a. This simply means a minus b. We get that the a minus b is equal to 1 and 5. Very easy, no? Now it says multiply the vector a by some number or scalar. So if we have the vector a, which is 3 and 4, if I multiply it by 2, what I expect is that this becomes 6 and this becomes 8. And this is actually what happens. But of course I can multiply it by some other number, so it doesn't need to be a natural number to do this. Also, it can be a negative number. Now it says multiply vectors element-wise. So as I already showed you, multiplying vectors element-wise, it gives you a Hadamard product, and it's something that we did not actually learn in school usually. So to compute the Hadamard product of a and b, I can just type a times b. And as you can see, it will just multiply the respective components. So x component times x component, y component times y component. And now it says compute the dot product by using code. So compute the dot product of a and b by multiplying two vectors element-wise and summing the multiples. For summing, use the numpy function np.sum. So what does this mean? So I have vector a. Okay, this is 3 and 4, and I have vector b, 2 and negative 1. So I need the vector product. So I need 3 times 2, and I need 4 times negative 1, and then I need to add this. 3 times 2 is 6 to negative 4, and I will get 2. So how can I do this? Well, if I do the Hadamard product, so a times b, then this will give me 6 and negative 4. So I just somehow need to add this 6 and negative 4. So how can I do this? Well, I already got the tip here. So just use the np.sum function. So if I do np.sum of this Hadamard product, what will happen is all of the components of the vectors will be added together. So 6 will be added to negative 4. And I will get that the dot product between these two vectors is equal to 2. And now it says apply the last operation, this one, to compute the length of the vector a instead of using the Python's embedded function lineage.norm. Okay, how can we do this? Well, we know that the vector a has horizontal component 3 and vertical component 4, and to compute the length, we need 3 times 3 plus 4 times 4, and then take a square root of that. So to achieve that, we can just use the Hadamard product. We can multiply the vector by itself, which gives us the Hadamard product of vectors a with itself, and then we get the sides squared. So 3 squared is 9, and 4 squared is 16, and we just now need to take the sum of these two values. So I can type np.sum of a times a, which gives us 25. Finally, we just need to take the square root of this, and this will be the application of the Pythagorean theorem. So np.sqrt, which gives us the square root, and then this gives us that the length of the vector a is 5. If I wanted to find the length of the vector e, I could just type np sum of e times e, and then take the square root, and you got the vector's length. Well, amid all the possible vectors that can be represented in the space of given dimensionality, some vectors will be more unique than the others. And those vectors are called basis vectors, and we can think of them as the elementary units constituting the given vector space. And just like with numbers, we have the number 1, and this number 1 is a special number. It is called an identity element for multiplication. For example, any number we multiply by 1 gives us this same element. So in linear algebra, this role is played by basis vectors. And since our example here on the screen is in 2D, well, we will have two basis vectors constituting this space, and they are called I hat and j hat. I hat has the coordinates 1 for the first dimension and 0 for the second dimension, and j hat has the coordinates 0 for the first dimension and 1 for the second dimension. And these two vectors are orthogonal. If we computed the dot product between them, you would see that 1 times 0 is 0, 0 times 1 is 0, 0 plus 0 is 0, so the dot product between these two vectors is 0, which guarantees that they are orthogonal to each other, and this is very important here. As we already know, in linear algebra, we can describe any vector by means of its projections. So we can describe the vector A by means of its horizontal projection 3 and its vertical projection 4. But what basis vectors allow us to do is to represent these vectors in terms of I hat and j hat. So to represent A, we can just take 3 I hats and add it to 4 j hats. And by making this so-called linear combination of these two vectors, we can describe any vector in two-dimensional space. But not only in two-dimensional space. If you have a three-dimensional space, which has 3 basis vectors, which is the minimal number of vectors constituting three-dimensional space, we can call them in this case I hat, and I hat now will have 3 projections, j hat, which will have 3 projections, and k hat, which will have 3 projections. And now if we have this vector with its projections 2, 3, and 5, we can use a combination of I hats, j hats, and k hats to reconstruct it. So we just need to add 2 I hats, 3 j hats, to 5 k hats, and we will reconstruct fully this vector. Here on the bottom we see our common representation of vectors a to e. But as you can see, if we know the basis vectors of the given space in which they are represented, then we can describe these vectors as a linear combination of the basis vectors. So instead of representing A as a vertical arrangement of numbers 3 and 4 within square brackets, I can represent it as a linear combination of I hats and j hats. So I take 3 I hats and add to it 4 j hats. And I can do that to any vector that I can represent in square brackets. What is very important about these particular vectors I hat, j hat, and k hat is that they are orthogonal to each other. And their linear combination can describe any vector in the given space. For example, in two-dimensional space, we have I hat and j hat. By making a linear combination of I hat and j hat, I can represent any two-dimensional vector. So I can fill the whole 2D space with vectors. And in 3 dimensions, I have I hat, j hat, and k hat. They are orthogonal to each other. Therefore, I can use them to represent any vector in 3-dimensional space. Why is this possible? Well, this is possible, for example, in 3 dimensions because neither of these vectors themselves can be described as a combination of other two. So I cannot use I hat and j hat to represent the k hat, or I cannot use j hat and k hat to represent I hat. Simply, they point in different directions, and whatever I do by using 2, I cannot reproduce the third. And the vectors, in set of vectors that have this property, we can call them linearly independent vectors. So without going into details, because we do not have time, every new vector that you introduce in the space and you want it to be the basis vector, it has to introduce a different direction, a new direction which cannot be described by the previous vectors that you took to constitute the given space. Also, to understand what it means to have linearly independent vectors, we can look at the other side, linearly dependent vectors. So linearly dependent vectors in a set of vectors, this would be those vectors that can be described by a linear combination of the others. Now let's see a concrete example. On this image, we have 3 unit vectors. This means that the length of these vectors is equal to 1, and they are all located into a plane. So this is not a 3-dimensional space that I described here, it's a 2D plane with 3 unit vectors. So the first thing that I might try to do is to describe the vector p by using unit vectors I hat and j hat. And of course I can do that. I can take negative 0.88 of the I hat, I can take negative 0.47 of the j hat, I can add them together, and this will give me p hat. But this is not the only thing that I can do. I can also use I hat and p hat to describe the j hat, although they are not orthogonal to each other. It's just the parameterization of these basis vectors will change. So I can use negative 2,13 of the p hat, and I can take negative 1,87 of the I hat. If I add them together, I can fully reconstruct j hat. And also, I can describe I hat by means of p hat and j hat. I can use negative 1,14 of the p hat and add to it negative 0,52 of the j hat. When I add them, I reconstruct fully I hat. It is very important to realize that any two of these 3 unit vectors can be used to fully describe 2D space. I do not have to use 2 vectors that are orthogonal to each other, and they do not have to be I hat and j hat. They can be any 2 vectors in 2D as long as they are not parallel to each other, because if they are parallel to each other, the only thing that I can reach by combining them is something which will be on a single line. They will not be able to reach any point in 2-dimensional space. Here we have 2 vectors, u and v, and they are parameterized by some numbers. So then what we will do is we will make a linear combination of u multiplied by some scalar and v multiplied by some scalar, and we will try to reach as many points as we can with this linear combination. So we call a set of all the vectors that can be described by this linear combination, we call it the span of the vectors u and v. So to fully span 2-dimensional space, u and v need to be linearly independent. If they were parallel to each other, then we will only be able to span a line within this 2D space. But if they are linearly independent, I want to show you with this animation that we can in principle reach any vector within this 2-dimensional plane by means of this linear combination of u and v. You might be wondering what happens in higher dimensions. Well, to fully span 3-dimensional space requires us to have 3 linearly independent vectors. So they do not have to be orthogonal to each other. It is just important that with any 2 of these vectors, you cannot reconstruct the third one. So what we have on this image is 2 linearly independent vectors, yellow one and the green one, and we have the purple one, which is a linear combination of them. So we have 3 3-dimensional vectors, but one of them is linearly dependent on the others. Because of that, this linear combination of these vectors can only span a plane within the 3-dimensional space. So only a single plane. It cannot reach anything outside of this plane. So to reach all of the points in the 3D space, this purple vector will need to leave the plane. So now that we know this, we can give also a technical definition for what is a vector basis. Well, it is a set of linearly independent vectors that span the full space. So in 3D, this would be a set of 3 linearly independent vectors. They would be spanning the full space. In 2D, we would need to have 2 linearly independent vectors. The other very important mathematical object that we will investigate in linear algebra is a matrix. At the beginning of the class, we introduced a convention of representing vectors as an ordered vertical arrangement of numbers within square brackets. So we have a number of vectors here, and they're all organized in a single column. Representing vectors like this is a part of a broader convention of orderly arranging numbers in a rectangular, table-like structure, which we call a matrix. The convention when describing a matrix is to always start with the number of rows and then go to the number of columns. With this convention in mind, we can represent this matrix as a 3 times 4 matrix, or the matrix which has 3 rows and 4 columns. So what is this arrangement of numbers about? Well, there is not a single precise meaning associated with matrices, because above all, they are a mathematical structure which uniquely arranges numbers. Let's think about numbers for a second. We can use numbers to count, but we can also use numbers to measure. We can use vectors to describe a direction and a magnitude of a force. For example, we can use it to represent a force on a beam, but also we can use vectors to encode certain object computationally. For example, we can use a vector of RGB components to represent color in a computer. And consequently, we can use this rectangular arrangement of numbers to do many things. We can, for example, very concisely represent a system of linear equations called an augmented matrix. Or we can conveniently represent any kind of linear transformation of space. But these specific uses that I just mentioned, they do not exhaust what this structure can ultimately facilitate. It is more that we can kind of find a way to use this ordered table of numbers to accomplish something either more efficiently or to describe something in a way that kind of ends up illuminating what we do from a new perspective. And this will definitely happen with neural networks. And when this happens, when we use this matrix and this illuminates our way of doing something, then we tend to associate a very specific meaning to these mathematical objects. What we must not forget in this case, that this is really a matter of perspective. So matrices themselves, they are not specific to the way you use them. In linear algebra, matrices extend the idea of just manipulating vectors in space towards manipulating the whole space. So, of course, this space then includes all the possible vectors in it. So to explain this, we will use the idea of linear transformation, and we can think of a linear transformation as a function which have certain properties that can transform an input which can be defined in terms of vectors into an output defined in terms of vectors. So here we have the vector input defined by three projections x-old, y-old, and z-old, and we can use a linear transformation which can be represented by a matrix, and then by applying a linear transformation to this vector we get the new vector which has projections x nu, y nu, and z nu. Well, what would be the properties of a linear transformation? Well, the most obvious property is, the name says, linearity. And linearity is something that is defined very formally in mathematics, and this is not crucial for us right now. What is crucial for us is to what kind of interpretations this formal definition leads. And I can tell you that this formal definition can be interpreted in many ways, and some of them are geometric. And let's try to describe one. So imagine that we have a two-dimensional plane, and the plane itself, because it's shapeless, you can think of it as a kind of empty canvas. In order to illustrate its principal directions, we need some kind of a helping device, and one of these devices is a coordinate axis, which we put here on the screen. And another device is a grid. And the grid subdivides the space with two sets of lines. One set is parallel to one coordinate axis, and the other one is parallel to the other coordinate axis. And here we placed the axis in the center of this grid. Also, we encoded some objects within this structure, just to show you what is going on. Now we have applied a linear transformation to this space and all the objects in it. Of course, we could transform space in many ways, but there is a specific way in which a linear transformation transforms the space. So, what does linear transformation do? It does not move the coordinate center. So the coordinate center remains fixed at the coordinate, in this case, 0, 0. And what it also does is keeps the grid lines parallel to each other and equally spaced. But as you can see, the objects themselves are transformed. The little plus sign got skewed, and also the circle now became some kind of an ellipse. But the most importantly, our basis vectors I hat and j hat, they have changed. So on the left, you see our original space before it was transformed, and on the right you see the transformed space. So you might think that this is kind of a different camera looking at the same space, but no, this is not what is going on. The space itself had been a little bit rotated and stretched and skewed, which then of course means the objects in it will also be transformed, scratched, and skewed. Well, the nice thing about linear transformations, apart from some other types of transformations, is that they are very easy to encode. So however we decided to linearly transform the space, this can be captured by only taking a note of what happens with the basis vectors. So our basis vectors here are I hat and j hat. And to capture what happens in the transformation of the space, we just need to track I hat and j hat and see where they land after the transformation. As you can see, now I have transformed this space, and the I hat new landed at the coordinates -1 and 3, and the j hat landed at the coordinates -2 and -1. These four numbers are sufficient to describe this linear transformation of space. How can we do this? Well, we need to store them in the matrix. The first column of this matrix will store where the I hat lands, and the second column will store where the j hat lands. And this rectangular arrangement of numbers is now sufficient to tell us where any vector in the original space will be landing when we transform the space, and this is very powerful. Some linear transformations are used very often, especially in computer graphics, and a good example is to use matrices to rotate a space in a specific direction. So let's see how we can do this. Let's say that we wanted to rotate the whole space 90 degrees clockwise. So on the left is our original space, and on the right is our transformed space. As you can see, both I hat and j hat are rotated around the origin for 90 degrees. So the only thing that we need to do to describe this transformation is to capture their new projections. So I new will now be located at the coordinates 0 and -1, while the new j will be at the coordinates 1 and 0. So we can use this matrix to encode this rotation. If we wished to rotate the space 90 degrees counterclockwise, we just do the same thing. We rotate I hat and j hat 90 degrees counterclockwise around the origin. We get that the I hat lands on 0 and 1, and the j hat lands on -1 and 0. And then we get a matrix which fully describes the rotation of the whole space 90 degrees counterclockwise. Another useful rotation is called a shear transform. As you can see, after applying the shear transform, I hat remains where it was, but j hat goes towards the direction of I hat. So its new coordinates are 1, 1. So now we have a matrix describing a shear transform of the whole space. And now we have a transformation that actually does not transform the space at all. It just leaves it as it is. So it is a matrix which contains the original basis vectors. So I know what you might be thinking. What is the use of a transformation which does nothing to the space? Well, wait a little bit. This is the same as if we said, well, what is the use of the number 1 in multiplication when whenever we multiply 1 by any number, we get that same number? Well, when that actually happens, then we know that this number or this structure is actually more important than all the others. It has some very fundamental properties it brings to the table. So what is characteristic for this identity matrix is that all of its elements are 0 except the ones that are in the diagonal. So if we had the identity matrix in 3 dimensions, it would look like this. So the diagonal elements would be equal to 1, and non-diagonal elements will be equal to 0. So it has some nice numerical signature, which is very important. Well, now let's look at how these linear transformations actually look like. We will have a certain vector in the space, and then we will transform the space, and what we want to know is where will this vector end up in the new space, in the transformed space. So what we have here, we have the coordinate system, and we will introduce also the grid. And the grid lines are spaced 1 unit from each other. Now, into this space we introduce the vector p, an arbitrary vector. In this case, the vector has an x-coordinate -0.5 and the y-coordinate -1,5. Of course, in this space we have our unit vectors I hat and j hat, I hat having coordinates 1 and 0, and j hat having coordinates 0 and 1. Another way to represent the vector p is as a linear combination of I hat and j hat. So what we need to do is take -0.5 of I hat and add to it -1,5 of j hat, and then we can reconstruct the vector p as a linear combination. This would be another way to describe the same thing. Instead of now we represent vectors in square brackets. Well, this is our old space, and the vector p lives in this old space. And now we want to transform the space. So to transform the space, we only need to keep track of what is happening with the basis vectors I hat and j hat. And now our I hat and j hat, after the transformation, land to some points which can be described in terms of the old space. So I hat new lands on the point -1 and 3, and j hat new lands at the point -2 and -1. We are still not describing the new space, we are just kind of preparing what will happen after the linear transformation. So what we are interested to know is what will happen to P after the transformation. Where will this P new land? So what we need to do now is we need to encode this linear transformation within a transformation matrix. So to do that, we take I hat new and place it into the first column of our matrix, and then we take j hat new and place it as the second column of our transformation matrix. When we apply the matrix to the space, the whole space gets transformed, and now I hat new and j hat new are the basis vectors of this new space. On this picture, I still haven't removed completely the old space. You can still see the grid lines, although they are now marked in light gray. So how can we compute the coordinates of the P new? Well, the consequence of this linearity that the transformation preserves is that our new vector P new will still remain parametrized by the same scalars which multiply I hat and j hat. Only this time our parameters negative 0.5 and negative 1.5 will multiply the new basis vectors I hat new and j hat new. And this is another way how we can describe it. We keep the old parameters, but now we have placeholders to put new basis vectors. And where can we find these new basis vectors? Well, we can find them in our transformation matrix. We take the first column from the transformation matrix and multiply it by negative 0.5, and we take the second column from the transformation matrix and multiply it by negative 1.5. And now the only thing we need to do is add and multiply some numbers. So negative 0.5 times I hat new will give us the vector with coordinates 0.5 and negative 1.5, and the negative 1.5 times the j hat new will give us the coordinates 3 and 1.5. When we add these two vectors together, we get that the coordinates of the P new in terms of the old space are 3.5 in the x direction and 0 in the y direction. And now we can use this to plot the P new. So we used to have vectors I hat, j hat, and p, and after the transformation we now have I hat new, j hat new, and p new. Well, if you now look at the picture of this new space, you will realize that the relation between new basis vectors and the new vector p has not changed from the previous situation. You can still use negative 0.5 of I hat new and negative 1.5 of j hat new, add them together to completely reconstruct the P new. And this is exactly the same as in our last case, where you could take negative 1.5 of j hat and add to it negative 0.5 of I hat to fully reconstruct the vector P. So the main property of a linear transformation in terms of the transformation of space is that the parameterization of our basis vectors do not change. The only thing that changes after the transformation are the basis vectors themselves. So now that we have all the results of our linear transformation, let's see how we can describe this symbolically. To compute the P new, we need to multiply the vector P by a transformation matrix M. And this is how we will do it. The transformation matrix M needs to be on the left side of our vector P. So when we replace the variables with numbers, we get kind of a weird constellation of numbers making an equality. So the purple thing being equal to the black thing. And what is this thing on the right? Well, this thing on the right is actually a case of a matrix multiplication. Well, then you might ask, well, this thing, negative 0.5 and negative 1.5, well, this is a vector, this is not a matrix. Well, we can think in these terms of a vector of being a matrix with only a single column. So vector is a special case of a matrix then. So what we have seen is how a single linear transformation transformed the space. But what if we wanted to compose more than one linear transformation? How can we do it? So our task is to rotate the vector q, whatever it is, 90 degrees counterclockwise, and then apply the shear transform to the result. So now we can already know that this vector q is a two-dimensional vector. So we have q. So what we need to do, we need to apply a transformation which rotates the whole space 90 degrees counterclockwise. After this transformation, we can call the new vector q rotated. And then we want to apply the shear transform to the result, which means we need to apply the shear transform to the Q rotated. We apply the shear transform to the whole space, in which also Q rotated lives, and we get the Q final. So this will be the vector after two linear transformations. So let's describe this symbolically. So we have a matrix which represents the counterclockwise rotation. We call it M rotate 90 minus. Then we multiply the vector Q by this matrix, and then we get Q rotated. Then in the next step, we need the matrix for the shear transform, and we will call this matrix M shear. So what we do is we take the Q rotated and multiply with this new matrix. This results with the vector Q final. So we needed to do a couple of steps to actually finally reach the vector Q final. And this is how this can be visualized. We start with the vector V, which is the red vector. We rotate the space, and then the vector gets rotated to its new position. And then we apply the shear transform to this new space, and then the shear transform actually places the vector somewhere else. So the vector Q final is now in its final position, the gray vector. So an interesting question to think about now is, can we create a transformation that does both rotation and shear at the same time? Actually, this can be done. What we need to do is we need to multiply the matrices standing for these two linear transformations together. So the matrix on the right needs to be the transformation which we apply first, and the matrix on the left needs to be the transformation that we apply last. And the operation of multiplying these two matrices is called matrix multiplication. And we do not yet know how to do this, but bear with me, we will learn how to do this. The most important thing to realize now that if we know how to multiply these things, and if we multiply them, we will end up with a matrix that will represent a transformation of space which includes both rotation counterclockwise and shear transform at the same time. So now if we multiply this matrix with our vector Q, we instantly obtain the vector Q final. So there are no extra steps in between. So this is a very nice property of linear transformation. Instead of working with them serially, taking a vector, then applying the transformation, getting the output vector, and then multiplying the output vector with another transformation, we can instead multiply the linear transformations themselves by using matrix multiplication. So in this way, we can represent a fairly complex transformation of space by means of multiplication of matrices. Finally, let's visualize what we did so far. We took the vector V, we first rotated it, and then applied the shear transform to it. Well, the same thing can be achieved by using only a single matrix. And this matrix needs to be a product of the matrices which were used for previous transformations in a certain order. And now the only thing that we are left to do is to learn how to actually perform matrix multiplication. And here we have a matrix A, which have 12 elements. Let's see how these elements within this matrix are indexed. How do we name these elements in the general case? Let's take the element A22. So the numbers 2 and 2 actually only mean indexing by rows first and then by columns. So this particular element is in the row number 2 and in the column number 2. So to perform matrix multiplication, we need to have two matrices. Let's introduce another matrix B, which has 4 rows and 2 columns. Before we can actually multiply matrices, we need to check if they are actually compatible, because not all matrices can be multiplied with each other. Let's first check what are the dimensions of these two matrices. The matrix A has dimensions 3 times 4, which means it has 3 rows and 4 columns. The matrix B is of the size 4 times 2, which means it has 4 rows and 2 columns. And now comes the first rule of matrix multiplication. To compute the matrix product A times B, the number of columns of matrix A needs to match the number of rows of the matrix B. Well, this is very simple actually, although it can sound convoluted. Well, as you can see, the matrix A has 4 columns represented by 4 vertical lines, and the matrix B has 4 rows represented by 4 horizontal lines. Where are these numbers of columns and rows actually reflected on our description of the matrices? Well, as you can see, in case of the matrix A, this is the right number is number 4, and in terms of the matrix B, this is the left number, which tells us the appropriate number. So if we write our matrices A and B next to each other, if these inner elements are equal, this means that two matrices are compatible for multiplication. And in this case, indeed, they are compatible. So we can go to the next step. Well, in the next step, we need to define what will be the size of the final product matrix. So the product matrix will have the same number of rows as the matrix A and the same number of columns as the matrix B. And this is very easy to see if we actually mark the rows and columns on the image. But where is this reflected in the dimensions of the matrix that we extracted before? Well, in the case of the matrix A, this is the leftmost number, and in case of the matrix B, this is the rightmost number. So these numbers tell us that our matrix C, which is the product matrix of matrices A and B, will be of the size 3, 2, which means it will have 3 rows and 2 columns. Let's now put all of these 3 matrices together. We already know how to index all of 3 matrices. We know the size of the matrix C. The only thing that we do not know is how to actually compute the elements of the matrix C. So how to compute, for example, the elements C21, which is the element in the second row and the first column of the matrix C. Well, the computation of any element of the matrix C actually involves only one mathematical operation, which is dot product. We simply need to compute the dot product of the red arrangement of numbers with the blue arrangement of numbers. So to compute the value of the element C21 means that we need to take the second row of the matrix A and do a dot product with the first column of the matrix B. This means C21 is equal to A21 times B11 plus A22 times B21 and so on and so forth. Let's do another element. If we wanted to compute the value of the element C32, this means that we take the third row of the matrix A and do a dot product with the second column of the matrix B. And they, of course, need to have the same amount of elements. And this is ensured by doing the compatibility test first. So then C32 will be equal to A31 times B12 plus A32 times B22 and so on. Well, now that we know how to do this, you can see that it's a kind of a long mechanical operation that takes place. So let me just show you an animation of how all the elements are computed. So C11, C21, C31, C12, C22, C32. If we actually wanted to describe all the computation that goes on to compute the elements of the C, you will see that this matrix looks a little bit scary. But if you look more closely, you will just see that it's just a bunch of addition and multiplication. So just a bunch of dot products which is taking place there. So this leads us to the conclusion, which is that matrix multiplication should be done by computers. This is not a job for a human unless you do not have a computer to do it for you. This is simply a mechanical task that should be automated, and this is what we will actually do. Before we start with the exercise, let's just cover the other simpler matrix operations that we did not do yet. So one of them is matrix addition, and as you can imagine, this is a very simple operation. In order to add two matrices together, they first of all need to be of the same size. If they are of the same size, then you can just add the respective elements together. This means you need to add element A11 to the element B11, element A12 to the element B12, and this is done until you add all of the elements within these two matrices. Matrix subtraction is not very different, you just need to subtract the corresponding elements. So A11 minus B11 gives you, for example, C11. Finally, to multiply the whole matrix by a number, the only thing you need to do is take all of the elements from this matrix and multiply it by this number. Now we can continue with the exercise number 10, which now comes to matrices, and we have elementary matrix operations in Python. It says, let us define matrices A, B, and C as follows, and we have 4 matrices here. It says, the first task is to use NumPy's data structure called array to represent the matrix A. And here we have matrices B, C, and D already represented. So what can I do? I can just make an array, mp.array, and then I will open the square brackets, and let's just add the rows first. So the first row will have elements 4, 2, -1, 5. Then I will add comma and just copy paste this 3 times. Comma. Okay. The second row has the elements 2, 1, 3, and -3. And the fourth row has the elements -2, -3, 1, and 4. So it is not necessary to indent this 3 spaces or 2 spaces, I just do it for clarity's sake, so to look better. And now I need to surround this structure with another pair of square brackets. If I do this, I get the matrix A, and I just need to assign it to a variable, and I will assign it to a variable capital A. Okay, now it says here we define the other matrices, so this is a kind of quite straightforward operation that we did here, so it's not necessary to do all of them, so I did it for you, so that we can now actually think about the operations. The next task says print the variables containing the matrices to make sure they match the definition. So I can just say print A to make sure that this thing is equal to this thing. So 4, 2, -1, 5, 2, 1, 3, -3, -2, -3, 1, 4. So it seems to work. B, C, D. All right. Now it says add matrices A and B and I'll analyze the result. So let's add A to B. As you can imagine, the operation is the same as with vectors, because vectors are indeed a special case of matrices which have only one column. So this should work. A plus B. Let's see what it is. Oh, it doesn't seem to work. It says value error, operands could not be broadcast together with shapes 3, 4, 4, 3, 2. What is Python telling me here? What is this shape? Well, as you can see, if I type a.shape, this tells me that the size of our matrix is 3, 4, which means it has 3 rows and 4 columns. And the matrix B has 4 rows and 2 columns. Well, these matrices, obviously, as you can see here, they don't have the same size, so we cannot add them, because this element, we would not know what to add it to. There is no corresponding element in the matrix B. Therefore, vector addition is not defined for matrices that do not have the same shape. Therefore, this error is actually something that you should expect to get. You cannot add these matrices. So it says add the matrices C and D. C plus D. As you can see, you get the result, so there's no error. Let's check why is this happening. Well, C and D, obviously, they are both square matrices, square meaning that they have the same number of columns and rows, so these are 2 square matrices. They obviously have the same shape, so we can add them together. It says add the matrix A to itself. Well, this is interesting because it is guaranteed to give us the result, because simply we know that matrix A and matrix A have the same number of rows and columns, as it is the same thing. And this would be, of course, the same as if I multiply this matrix by a number 2. And this is what comes next. It says multiplying a matrix by a scalar in Python. Multiply the matrix A by 5. Well, I take A and I multiply it by 5. And I get the matrix. So this means that each of these elements is now, if we divided it by 5, we would get the original matrix A. So just take all of these elements and multiply it by 5. If we multiply it by 2, we would get the same matrix as if we added A plus A. So now it says multiply the matrix by -5, so A times -5 just gives us the matrix which has all the elements multiplied by -1 in terms of the original matrix. So if this here you have 20, here we have -20. If we have -15, here we have +15. And now we have matrix multiplication in Python. Compute the matrix product A times B by using the numpy command mp dot and analyze the result. Well, this is interesting. The matrix product, as we have defined it, in numpy is implemented with the function dot. So it kind of tells us that this is actually a special case of a dot product. Well, the dot product that we defined in terms of vectors is actually a special case of a matrix product, only a simpler one. So we can think of a dot product if we apply it to non-vectors, to actually matrices, to be the matrix product. At least this is how it is defined in NumPy. So if I wanted to compute the matrix product of A and B in NumPy, I need to use the command mp dot dot. So let's do that. mp dot A comma B. Will this work or not? Let's see. Let's see if it's gonna work before we actually press compute. So the first matrix A has 4 columns and the matrix B has 4 rows. So if this matrix has 4 columns and this matrix has 4 rows, this tells us that these matrices are compatible so that we can actually compute the matrix product. So I'm assuming this will work. So if I run it, you can see that I actually got the answer, and I got that the product matrix has 3 rows and 2 columns. 3 rows comes from the rows of the matrix A, and 2 columns comes from the number of columns of the matrix B. And now this is interesting. We computed the matrix product A times B, but now it asks us compute the matrix product B times A and analyze the result. Well, what will happen? Are we guaranteed to get the result here? Well, not really, because A times B can be a valid matrix operation, and it is because we analyzed it and we realized that the number of columns of the first matrix is the same as the number of rows of the second matrix. But if you reverse the matrices, then this is no longer the case, because the B has 2 columns and A has 3 rows. So B times A is actually not possible to compute. They are not compatible. And then it says compute the matrix products B times C and B times D. Okay, let's copy paste B times C. What will happen there? Well, B times C, is this possible to do? Let's check. B has 2 columns and C has 2 rows, and also D has 2 rows. So I'm guessing that B times C works and B times D works. So B times C works exactly, and also B times D should work. So both of them work. And now it says again something interesting. It says compute the matrix product C times D and D times C. So last time we tried to do this didn't work. Will it work this time? Well, DC, maybe it won't work. Well, actually it works. Why does it work? Well, the reason because it works is that C and D are so-called square matrices, so they have the same number of rows and columns. And these kind of matrices are actually commutative in terms of the product. You can compute both C times D and D times C, but only if they are square matrices. In normal cases like this is not always possible. And this was all for our exercise 9. Well, the things that we learned today will actually help us to reach another level of abstraction in constructing our neural network algorithms. We will now need to see how to implement operations that we had in our computing our forward pass and our backward pass. How can we represent this by means of these matrix and vector operations? As you have seen, the vector operations are relatively easy to do, apart from the dot product, which requires you to actually know what you are doing. And on the other side, matrix multiplication can be quite complicated. It is not complex at all. It is a very mechanical thing, and you can learn it to do it very easily, but you need to think about what is going on there. And in order to follow what we will do next class, which is implementing neural networks by means of matrices and vectors, you need to know very well how to do a dot product and how to do a matrix product. So I really encourage you to practice this, because if you do this, next class will be relatively easy to follow. We will just do what we have done before, it's just we will represent it in a different way. But if until the next class you do not master dot product and matrix product, then it will be almost impossible for you to follow this course from the next class. So I really encourage you, please practice the dot product and the matrix product. Of course, you should practice also the other operations, but they are much easier than these two. This was all for this week. I hope you learned something. I hope you enjoyed it. I hope you find linear algebra as interesting as I find it. And see you next week. Goodbye.